Good morning, everyone. In this session, let us discuss one more algorithm, that is A-star algorithm, which comes under informed search or heuristic search. So in the last class, we discussed about greedy best first search algorithm. In this session, let us discuss about this A-star search algorithm. So A-star is the most commonly known form of best first search. We know that it already uses the heuristic function h of n and cost to reach node n from the start state g of n. Not only h of n, along with h of n, it also uses the cost. And it has combined features of UCS, that is Uniform Cost Search, and Greedy Best First Search, by which it solves the problem efficiently. And A-star search algorithm finds the shortest path through the search space using this heuristic function. This search algorithm expands less search tree and provides optimal result faster. And it is similar to UCS, except that it uses a function g of n plus h of n instead of g of n, where we are going to use this concept in greedy best first search algorithm. In A-star search algorithm, we use heuristic search as well as the cost to reach the node. We use heuristic plus cost to reach the node, and hence we can combine both costs as follows, and this sum is called as the fitness number, that is f of n equal to g of n plus h of n, where f of n is equal to estimated cost of the cheapest solution. G of n is cost to reach node n from start state, and h of n is cost to reach from node n to goal node. So this is h of n. With this formula, we are going to find out the path from start state to goal state using this A-star search algorithm. Let us see the algorithm of A-star search. The same similar like earlier greedy best first search. The only thing is the evaluation function is different. Come to step 1. You are going to place the starting node in the open list, and if the open list is empty or not, and if the list is empty, then return failure and stop. Same like that. Select the node from the open list which has the smallest value of evaluation function, that we are going to take it as path cost as well as heuristic function. And that expanded node itself is goal node, then return success and stop. Otherwise, expand node n and generate all of its successors and put n into the closed list. For each successor n, we are going to check whether n is already in the open or closed list. If not, then we are going to compute the same evaluation function for that particular n, and then we are going to place it into the open list. And else if node n is already in open or closed, then it should be attached to the back pointer, which reflects the lowest g of n value. And then we are going to return to the step 2. This process will continue until we reach to the goal state. So just let us have a look of this flowchart of A-star algorithm. We are first initializing the start node n, and then we are going to put it in an open list, and then we are going to calculate the cost function, that is f of n equal to g of n plus h of n, and then we are going to remove from open list and put in closed list, and we are going to save the index of n with the smallest value. And if this n itself is the target node, yes, we are going to terminate the algorithm. Otherwise, if it is no, then we are going to find the successive nodes of n which are not in the closed list. And then we are going to calculate the f for each of these nodes, and this loop will continue until we reach to the goal node. So let us understand more with the help of this example. See, this is one of the given graph. Okay, A-star algorithm which is informed, and this is the start state, and this is the goal state. And remember, this is the path cost, and these are which are there in red color. These represents the heuristic values. Okay, these are heuristic values, and these are the path cost. Let us start from the start node. We know that already algorithm how it is going to work. In the same way, directly we'll find the solution of this particular graph using A-star algorithm. That is, the very first start state is yes. If we open the node yes. Yeah. So first, let us find out the fitness of, we know that f of n equal to h of n plus g of n. Sorry, g of n. F of n equal to g of n. So here, so the very first of, we are going to find out this function for start state. We know that start state there is no path, that is 0, but we have already have a heuristic value, that is 14. So f of s equal to, it is 14. Now, when we expand the node S, we see this diagram, when we expand the node S, it is going to be, and it is also going to C. So, S to B, and it is S to C. So, when it is S to B, see here, the heuristic value is 12 and the path cost is 4. Okay. So, it is 4 plus 12, 16. And coming to the S2C, path cost is 3 plus heuristic value is 11. So it is 3 plus 11 equal to 14. Now we can expand further from SB and from SC. So if you expand S to B, we have F and E. If you expand S to C, it may goes to E or D. Let us see now. Let us expand S to B. S to B, it is going to F. S to B, it is also going to E. So when you go SB to F, see the values. SB to F, 4 plus 5 and the heuristic value is 11. That is, here you can write it as 4 plus 5 plus 11, which is equal to 17. Similarly, SB to E, 4 plus 12, heuristic value is 4. That is 4 plus 12 plus 4 equal to, sorry, it is 20, sorry, 4 plus it is 20 and it is also 20. Okay. Now, let us explore this S to SE to E, SE to D. See here, SC to E, SC to D. That is, when SC to E, it is 3 plus 10 plus 4. And when it is S to D, 3 plus 7 plus 6. Okay. Now, it is 4 plus 5 plus 11 equal to 20. And it is 4 plus 12 plus 4 equal to, sorry students, that is 3 plus 10 plus 4. Yes. See here, sorry. 3 plus 10 plus 4, 3 plus 7 plus 6. Okay. 3 plus 10 plus 4, it is 17. So, 3 plus 7 plus 6, it is equal to 16. So, out of all these paths, we have 16 as the least. So, we are going to follow this path. That is, now we are going to take the path SCD. So, see here. Now, we are going to have a path S to D. And after D, there is no other option. We have to go to E. Now, next one, SCD is going to E. And the value is, see here, 3 plus 7 plus 2 plus heuristic value 4. So, the values are 3 plus 7 plus 2 plus 5, okay, is equal to, sorry, 3 plus 7 plus 2 plus 4 equal to 16. See here, 3 plus 7 plus 2 plus 4. That only I have written here. So, it is 16. Now, once we reach to here, okay, there is only one path, that is the E is directly reaching to the goal state. So, now the next one is SCDE is directly going to goal state and the values are 3 plus 7 plus 2 plus 5, and here the heuristic value is 0. That is, the value is 3 plus 7 plus 2 plus 5. Okay. See, 3 plus 7 plus 2 plus 5. Okay. Which is equal to, and the heuristic value is 0, which is equal to the 70. Okay. So, in this way, we are going to calculate this one. Okay. There is also other way you can go. That is, see here, S2B, you can also calculate S2B to F, S2B to E. Okay. But we are going to, we are getting more value when compared to this. That's why we have followed this route. Okay. You can also calculate S2B to F to G, S2B to E to G. But this path is getting the least cost. That's why this is the given path. So what is the solution now? The solution is, the given path is, it is S2, S2C, C2D, D2E, E2G. Okay, with a fitness number of value 70. So in this way, the A star algorithm is going to work. So what is the difference between that greedy best first search and this one is, in greedy best first search, it is going to take into consideration only G of n value. Here, along with the G of n H of n value, here along with H of n value, it is also going to consider the value of G of n. Okay, and it guarantees us optimal solution. Okay, whereas this best first search doesn't guarantee the optimal solution, but whereas A star algorithm is, that's why we call this A star algorithm as admissible. What do you mean by this admissible is, it guarantees optimal solution. That's why we can say that this A star is an admissible. So in this way, we are going to calculate the path from start state to goal state using this A star algorithm. So let us see the advantages of this A star algorithm. It guarantees finding the optimal path when used with appropriate heuristics. We have a exact appropriate heuristic. Yes, definitely it guarantees us optimal path. It is efficient and can handle large search spaces by effectively pruning the unpromising paths. And one disadvantage is that A star can be computationally expensive in certain scenarios, especially when search space is extensive and if there is number of possible paths is large. And another limitation of this A star is it heavily relies on the quality of the heuristic function. And if any heuristic function is purely designed or does not accurately estimate the distance to the goal, obviously the algorithm performance and optimality may be compromised. Okay, these are some of the examples, students. You pause for a minute this and try to solve the path from start state to goal state using this A star search algorithm. This is one example, and this is another example, finding from start state to goal state. Okay. And this is one more important. Now this is a 8 puzzle problem. Now you have to find out from start state to goal state of this 8 puzzle problem using the A star search algorithm. Already with heuristic function, I told you how to calculate. Now, along with heuristic function, you should also find out the path cost, and then you have to find out the solution for this. This is one assignment example for you people. Just solve this A star 8 puzzle problem using this A star search algorithm. Thank you.